In this video, I will explain the topic related to Shannon-Hartley theorem and its proof. Shannon-Hartley theorem and its proof. Shannon-Hartley theorem. According to this theorem, the channel capacity is given by C is equal to the channel capacity of the continuous channels. It is given by C is equal to B log 1 plus S by N to the base 2 bits per second, where B is called as bandwidth of the channel. B is called as bandwidth of the channel. Bandwidth of the channel. S is called as a signal power. Signal power. And N is called as noise power. N is called as noise power. The noise can be Gaussian or impulse in nature. Generally, the noise is called as additive white Gaussian noise. The noise can be Gaussian, Gaussian or impulse in nature. Generally, the channel consists of additive white Gaussian noise. The channel, the noise present in the channel, the noise present in the noise present in the channel is additive white Gaussian noise. The statement, according to in the statement form, generally information rate is represented as small r into capital H, where small r is called as a number of messages generated per second, or number of symbols are generated per second, or number of samples are generated per second. H is called as a entropy of the source, either analog source or digital source. The unit of R is bits per second. It is same as channel capacity. C is equal to R. C is equal to R. Channel capacity of the analog channels. According to this formula, the statement is defined as maximum rate at which information can be transmitted over a communication channel of a specified bandwidth in the presence of noise. Maximum rate at which information can be transmitted over a communication channel. of a specified bandwidth of a specified bandwidth, B in the presence of noise. In the presence of noise. The presence of noise. That is additive white Gaussian noise. This is termed as this is termed as capacity of the additive white Gaussian noise channel. This is termed as capacity of additive white Gaussian noise channel capacity. Additive white Gaussian noise channel. That's it. These two, information rate and the capacity of the channel, both are same. The unit is in both the cases, the unit is the same, bits per second in both the cases. Maximum rate at which information can be transmitted over a communication channel. This is the channel. The channel capacity is C. That information is bandwidth of the channel is finite bandwidth B. The noise present in the channel is additive white Gaussian noise channel. Noise. Maximum rate at which information can be transmitted over a communication channel of a specified bandwidth B in the presence of noise, that is AWGN. This is termed as the capacity of additive white Gaussian noise channel. Proof. This one is the information source. The information source is analog one. Analog one. The information source generates some continuous time signal x of t. Continuous time signal x of t. The highest frequency component present in the x of t is B. The highest frequency component present in the x of t is B. X of t B is B. The signal x of t is sampled with the sampling period is or sampling rate. It is further assumed that x of t has a finite bandwidth B, so that x of t is completely characterized by its periodic sample values. X of t is completely characterized by its periodic samples. The signal power is represented by S, capital S. The analysis is totally based on random variable, capital X, and entropy of this analog information source is H of X. X of t is sampled at a sampling period is Fs. Fs is equal to 2Fm, that is equal to 2B. This is the channel. In the channel, a additive white Gaussian noise is present, that is represented by N of t. Noise power is capital N. Random variable of that noise is small n. The output of the channel is Y. The output of the channel is y, random variable y. Entropy of that output of the channel is h of y, h of y. Output signal is represented by y of t. Therefore, output signal y of t is equal to x of t is applied to this channel, x of t. X of t plus n of t. In terms of random variables, y is equal to x plus small n, x plus small n. In terms of power, signal power is s, noise power is n, output signal power is output signal power is output signal power is s plus n, s plus n. Bandwidth of the channel is b. B is called as bandwidth of the channel. Bandwidth of the channel. See the description of the continuous channel. Next one is capacity. Capacity of the channels are two types. Symbol capacity. Symbol capacity. Symbol capacity is represented by CS is equal to maximum of I of x comma y bits per. In this case, the symbols are nothing but samples, bits per samples. Next one, bits capacity. Bits capacity is equal to, or capacity of the channel is equal to CS into sampling rate Fs, bits per second. CS is maximum of A of x comma y. Fs is samples per second. Fs is 2 FM, 2 into beta bits per second. Symbol capacity bits per samples. Bits capacity is represented by C is equal to CS into middle. Bits capacity C is equal to CS into Fs. CS is maximum of I comma I of x comma y into 2b bits per second. If the signal power is S and the noise power is N, then the received signal is received signal with power S and the received signal with power S and the noise power with power is N. The joint entropy of the source is H of x comma N. This is the small n in terms of random variable. This one is a small n. H of x plus H of n by x. If the transmitted signal and the noise are independent, the transmitted signal, if the transmitted signal and the noise are independent, then H of n by x is H of n. H of n by x is H of n, small n. Okay. The received signal is sum of signal x and the noise n. We may write x of x comma y is equal to H of x comma n. h of x comma y, we know that h of y plus h of y by x, or h of x plus h of x by y. This one is h of x by y. H of x comma n is here a small n. H of x plus h of small n. H of x plus h of small n. This value is h of x plus h of small n. H of n by x is h of n. I rearrange this equation. H of x minus h of x by y is equal to h of y minus h of n. H of y minus h of n. H of x minus h of x by y is I of comma y is equal to h of y minus h of y minus h of n. Symbol capacity or sample capacity CS is equal to maximum of I of x comma y, that is equal to maximum of h of y minus h of n. In case of continuous channels, we use differential entropy. For continuous signals, for continuous signals, we use differential entropies. We use differential entropies. That is maximum of CSC is equal to maximum of h of y minus h of n. Now I will concentrate on calculation of h of y. H of y is the output channel entropy. H of y is equal to minus infinity to plus infinity f of y probability density function into log 1 by f of y, capital Y, to the base 2 ty. Probability density function of f of y suffix capital Y is equal to 1 by 2 pi sigma y square e power minus y minus mu whole square by 2 sigma y whole square. 2 sigma y whole square. This is the channel capacitance, not channel capacitance, probability density function. Probability density function of the channel output f of y. Next one is 1 by log 1 by f of y to the base 2 is equal to, this can be written as in terms of ln 1 by f of y capital Y log e to the base 2. Log x to the base 2 can be written as log x to the base 2 can be written as ln x into log e to the base 2. Here x is 1 by f of y that is ln 1 by f of y. Y is 1 by square root of 2 pi sigma y square into e power minus y minus mu whole square by 2 sigma y square, where mu is called as variance, log e to the base 2. It is equal to ln square root of 2 pi sigma y square into e power y minus mu by 2 sigma y square, 2 sigma y square into log e to the base 2. These two terms are, this is the one term, this is the another term. Okay, ln AB is ln A plus ln B, ln square root of 2 pi sigma y square plus ln e power y minus mu whole square, y minus mu whole square by 2 sigma y square log e to the base 2. That is equal to 1 by 2 ln square root of, square root is represented by 1 by 2 here. Here 2 pi sigma y square plus y minus mu whole square by 2 sigma y square. These two are cancelled. Log e to the base 2. This is the value of log 1 by f of y suffix capital Y to the base 2. In h of y formula, minus integral minus infinity to plus infinity. For continuous entropies, we use integration minus infinity to plus infinity f of y capital Y log 1 by f of y suffix capital Y to the base 2 into dy. Now calculate entropy. H of y is equal to minus infinity to plus infinity f of y suffix capital Y into log 1 by base 2 dy. Minus infinity to plus infinity f of y suffix capital Y log 1 by f of y to the base 2 is 1 by 2 ln 2 pi sigma y square plus y minus mu whole square by 2 sigma square into log e to the base 2 dy. Multiply this one entire term minus infinity to plus infinity integral over f of y 1 by 2 ln 2 pi sigma y square into log e to the base 2 dy plus integral over minus infinity to plus infinity f of y into y minus mu whole square by 2 sigma square log e to the base 2 dy. That is equal to 1 by 2 ln 2 pi sigma y square log e to the base 2 integral over minus infinity to plus infinity f of y dy plus log e to the base 2 1 by 2 sigma square integral minus infinity to plus infinity y minus mu whole square f of y dy. This entire one is sigma square. The sigma square and sigma square is cancelled. This entire one value is 1 because the sum of the probability density function value is integral minus infinity plus infinity. That value is 1. Final here is 1 by 2. H of y is equal to 1 by 2 ln 2 pi sigma y square log e to the base 2 plus 1 by 2 log e to the base 2. Simplify this one. One by 2 ln this value is 1 by 2 ln log x to the base 2 is equal to ln x into log e to the base 2. This entire term can be written as x is 2 pi sigma y square. X is 2 pi sigma y square here. Log 2 pi sigma y square to the base 2 plus 1 by 2 log e to the base 2. That is equal to 1 by 2 log 1 by 2 log this is the bits per samples h of I. But CS is equal to maximum of I of x comma y. That is equal maximum of h of y minus h of n. H of y is here. H of y is maximum of h of y is 1 by 2 log 2 pi sigma y square e to the base 2 minus sigma square is the variance. Sigma y square is the variance. Mu is the mean. Mu is the mean. Similarly, for noise signals, it can be represented as 1 by 2 log 2 pi sigma n. For noise is variance is sigma n square e to the base 2. For noise signals, mean value is 0. That is 1 by 2 log m minus log n to the base 2. That is log m by n to the base 2. 2 pi sigma y square E by 2 pi sigma n square E. 2 pi cancel, E cancel. Therefore, this is the bits for samples. This is the bits for samples. CS. CS is equal to 1 by 2 log sigma y square by sigma n square. Sigma output at the output of the channel, the variance is signal power plus noise power. For noise case, sigma n square is that is noise. CS is equal to 1 by 2 log sigma y square is s plus n by sigma n square is n to the base 2. That is equal to 1 by 2 log 1 plus s by n to the base 2 bits for samples. Bits for samples. This is the CS. Next, channel capacity in terms of bits per second. C is equal to channel capacity in bits per second. C is equal to sampling rate into CS. Sampling rate is 2B into CS. Bits per second. 2B into 1 by 2 log 1 plus s by n to the base 2. 2 cancel. Therefore, capacity of the analog channel CS not C is equal to, finally C is equal to B into log 1 plus s by n to the base 2 bits per second, where B is called as a channel bandwidth, S is the signal power, N is the noise power. This is the derivation related to channel capacity of the additive white Gaussian noise channel.